Good morning. Welcome to Chemistry 111. Today we're going to go over the test material for test 4 for chapter 4 and chapter 5. I had uploaded this onto Google Classroom as test 4 and test 5, as that was where they were located in the last year. So we're going to go and get right started. Okay. So what we have here is a basic light law problem for the first one. That black light produces UVA light, which is one of the most common light produced at a wavelength at 350 nanometers. What is the energy of light produced by this light bulb? Well, this has two little tricks in it. One, you have to make sure to convert nanometers into meters. That's probably one of the biggest problems. Second problem is you have to make sure you're answering the question. If you look at the answers, you notice the first one is in inverse seconds. Even if that is the correct frequency, hint, hint, it is, even if that was the correct frequency, that is not answering the question asked, that what is the energy of this light? So going about, how do we do that? Oh, shoot, no. How do we do that? Step one is to convert nanometers into meters. That's 10 to the 9th nanometers in 1 meter, given this 3.50 times 10 to the negative 7th meters. The next step is C equals lambda nu, rearranged to say C over lambda equals nu, which is 2.998 times 10 to the 8th meters over seconds, divided by 3.50 times 10 to the negative 7 meters. It's going to give us our 8.57 or whatever times 10 to the 14th inverse seconds. Lastly, to actually answer the question, E equals H nu. H is 6.626 times 10 to the negative 19th times 8.57. Sorry, not negative 19th, sorry, negative 34th times 10 to the 14th. You do that, you get 5.68 times 10 to the 0.68 times 10 to the negative 19th joules. So what we're looking right there, simply we turn wavelength into frequency, frequency into energy. We should be able to turn energy back into frequency, energy back into frequency, and frequency back into wavelength if needed. But watch out the units and always make sure you're answering the question. Come on. Okay. Skipping 2. 2 is a gas question. 3 is a lab question for a lab we're going to do next week. 4 is another gas question. 5 is our first on dealing with electron configuration. This one, which ions/ions would be represented by the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. So looking at that, what is that? Neutral. That neutral 3p6 is the electron configuration of the noble gas argon. If I look at each guy and move them the respective places over and see, do they match? Potassium would be 4s1. When you become potassium plus 1, you lose the 4s and it becomes p6. So potassium is a possibility. Scandium would be 4s2, 3d1, but it's lost 3 electrons. So it lose the 4s2, then it lose the 3d1, which leaves us back at 3p. So already we have 2 ones that are correct, so it's going to have to be all of the above, but let's check them. Chlorine would be 3s2, 3p5. But chloride, we add another electron, it goes into the 3p6. And the sulfur would be 3p4. 2 electrons moves it to the 3p6. All 4 of these compounds are isoelectronic, meaning they have the same number of electrons. Get used to that term. Isoelectronic means the same number of electrons. Different number of protons. Thus, they have different sizes, but they're same number of electrons. Number 6, property of light lab. We looked at the difference between light absorbed and light observed. If potassium permanganate, which we didn't use, produces a deep violet light color, what light would be absorbed? So if it looks purple or violet, the big V, what color should it absorb? So for this, we need to look at our Roy G. Biv chart. We have red, orange, yellow, green, blue, violet. The rule states that the color opposite of the observed color is the one that is chiefly absorbed. If you look across from V, is the color yellow. So yellow would be absorbed, the yellow frequency of light would be absorbed, which produces the deep violet shade. So Roy G. Biv, red, if it looks green, it must be red. If it looks orange, it must absorb blue. Vice versa. So that was number 6. That was something really easy if you understand that from the lab. Electron configuration chart. Some of these, 7 is just filling this in, but we can use this for many different things. You could look at how many electrons are paired. So you look phosphorus. Phosphorus has 10, 12, 15 electrons. So we'd put up, down, up, down, up, 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 down, 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 up, down, and then you'd have to put up, 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 or down, down, down. It doesn't matter which direction you choose. The important thing is they're all the same direction, and none of them are paired in that last row. All the same direction, and none of them are paired. That's all. Shouldn't be too hard. Obviously, you won't be able to fill one of these in on an online test, but you, with this picture in mind, you could easily answer questions about it. What's the full electron configuration of technetium? You have to find that on the table. That's right below manganese. on row number 5. Right below manganese on row number 5. I can't see the number from where I'm at. Okay, so it's not a big deal, because how I'm going to do this is I'm going to use the periodic table and work my way across. I may do this fast, but that's just because I know first 2 columns are S. Last 6 columns are P. The middle transition metals are D, and their number is row -1. So I'm going to work my way across. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Here's where it gets tricky. 3d10, 4p6. Now we're on the last row. 5s2, and now I need to call 4d. 1, 2, 3, 4, 5. 4d5. Everything else is just working my way across. The big difficulty is 4d, 5s2, 4d5, and we stop right at technetium. If I had said ruthenium, it would have been 4d6. And I'm just working my way across. If I've labeled this, that's S, that's P, that's D. Okay, with the the lanthanum and lutetium. Yeah. So with that case, I'm never going to ask you for lanthanum or lutetium, but if, for example, I asked you platinum, we'll go ahead and do platinum real quick. Platinum is right there, right next to gold and mercury. So platinum would look like this. So platinum, I'm going to go in here to platinum would be, so we're going 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Now we're on platinum's row. Here's where it gets the tricky part. 6s2. Here's where we hit lanthanum and lutetium. So we're dropping down into the F row. We got to say 4F14. Then we're going to go to 5D and platinum. 1, 2, 3, 4, 5, 6, 7, 8. It's the 8th one. And don't let this trick you. If you count barium straight to hafnium, you would say platinum is 7, but then you would say there's 15 elements in the down below in the F. But really, it's a weird, tricky little minx here that one of those elements, either lithium or lutetium, should be in the D. But which one goes in the D is kind of up for debate. So rather than stick one of them permanently there, we just kind of have it. So like we put the lutetium and lithium down into the F. But there is only 14 elements in the F. There's only 14 elements in the F. But that's how we would do platinum of the same variety. Remember, the F is row -2 because it's supposed to show up on row 4, and it's available on row 4, but it doesn't get used to row 6. That's a very good question. Okay, moving back over here. Where's okay? Okay, okay. 11. What element is represented by the following electron configuration? 1s2, 2p6, 3s2 is, let's say, 3p2. Yeah, 3p2. So 3p2. So going that 3s2 is magnesium, 3p2 is silicon. Just silicon. Aluminum is 3p1. Phosphorus is 3p3. Carbon is 2p2. I put all of the above there in case people get like all of the above happy. Like, oh, the one was all of the above. Maybe there's this one's also. No, there's only one answer here. There's only one answer here. So it's B, silicon. Okay, this one is also, number 12 is also a light lab law. It is not hard if you understand the concept. If you don't understand the concept, it could be a little tricky. It is saying, I have iron thiocyanate, which we didn't actually deal with this lab. We will eventually deal with. But if this is the concentration of this iron thiocyanate with a path length of 1, it gives us the absorbance of what, like 0.903. What is the extinction coefficient? This one is just a Beer's Law lab. Beer's Law says, it doesn't really matter what you write. A, absorbance is A, B, C, or A is epsilon L, C. The important thing is, it's just 3 things multiplied together is equal to the absorbance. Your absorbance, 0.903, is equal to the extinction coefficient times 1 times the concentration. Concentration is that number in M, big capital M. Concentration is looking at the mole density. 10 to the negative 5th, is that what it says? Oh, thank you. So we always set the path length as 1 because we have control of what is the cell size. We are trying to make this as easy as possible, but we have to take that into account because you could have a larger cell. In this particular case, where all it comes down to is 0.903 divided by 4.3 times 10 to the negative 5th. You can include the 1 in there, but the identity property says any number divided by 1 is the number itself, so you don't have to. But that's going to give us epsilon. It's going to give us epsilon. So you take that, you divide by a small number, you get a big number. See, remember this one? 903. 0.903. It's like you get 2, 1, 0, 0, 0. 21,000. So this is a really high extinction coefficient. You don't need much concentration to get a really high absorbance. You don't need much concentration to get a very high absorbance. And that is, I could easily ask you, what is the concentration given this extinction coefficient? The only thing you would change is instead of dividing by the concentration, you would divide by epsilon. I could just as easily ask, what would the expected absorbance be if I gave you the extinction coefficient and the concentration? You would multiply those two numbers together and give you absorbance. The only thing to keep in mind is there is no units of absorbance. I'm going to leave this like this for the next problem. Write the condensed electron configuration of the following elements: scandium and tin. So for each of these guys, you find where it's at in the periodic table, and you take the noble gas from right above it. So scandium is row 4. So the row 3 noble gas is argon. So I start with argon as my starting point. Moving to row 4, you have 4s2 3d1. That is scandium. Tin. Tin is on the 5th row. The 5th row, below carbon, below silicon, below germanium, there's tin. So the 4th row, noble gas is krypton. Krypton, 5s2 4d10 5p2. I'm just working my way across. I'm not performing magic. I'm not doing brain surgery. Just working my way across. I do have the advantage that I remember the row numbers, so I can look at it and go, oh, rubidium is on row 5. So I don't need to label that. I got it already there kind of in my head. So, but literally I'm just working my way across. Row 5, rubidium. 5, there's 2 elements there, S2. I'm into the D's. So 5 minus 1, 4. D, all the way to cadmium, that's 10. Now I'm back into the P's, row 5, so it's 5p, bump, 5p2 gets me to 10. So, this is a light, this is a gas question. Here is another light question. This one is actually rather easy because if you were paying attention on the first question, this wavelength is not too dissimilar. Blue laser light can be produced by excitation of gallium nitride semiconductor to produce a 405 nanometer light. What is the frequency of this light? You could cheat. You really could cheat if you remembered what was the frequency of 350 nanometer light, because it's not going to change by a whole lot. They are pretty close. So if you remember, you can actually just jump a step and write your answer. Especially considering all of these answers are by multiple large factors of a difference. If I had 2 or more numbers that were close by any scope of the imagination, yeah, it'd be a little bit harder and you'd have to do this. But the idea is all these numbers were gettable. So first, I turn 405 nanometers into meters. 10 to the 9th nanometers, 1 meter. You got 4.05 times 10 to the negative 7th meters. Then you take the speed of light, 3 times 10 to the 8th meters per second, divided by 4.05 times 10 to the negative 7th meters, give you your answer. Without even doing the math, I can tell you the answer is C. 7.4 times 10 to the 14th hertz. Real quick conversion. 1 inverse second equals 1 hertz. It's a 1-to-1 conversion. 1 inverse second equals 1 hertz. So, and it's given. I'm always going to give that to you. But so you would get 10 to the negative 14th inverse seconds. So you can turn that to 10 to the negative 14th hertz. But so that is that guy. Wavelength of light. That's a gas question. This, I'm not going to ask this of you, but you, because this is a kinetic energy problem, it's not really that hard, but I will go ahead and work through this. We are not going to do the second part of this one on the test, but I'll go ahead and give this to you. So zinc or whatever has a photoelectric effect, has a work function of 5.82 times 10 to the negative 19th. Based on the number of this number, what would be the energy? So what's the energy of the 285 nanometer beam of UVB? And what kinetic energy would the electron shot off be if there's no electron? So essentially, first question, E equals H nu. Calculate that. Second question, kinetic energy equals E minus the work function. I'm not going to ask that of you on the test, but we could do that. We could definitely do the first part. Definitely do the first part. So with that in mind, let's say based on 285 nanometers. So right now, erasing some of this. 285 nanometers gives you 2.85 times 10 to the negative 7th meters. So all this is very repetitious, very, very repetitious. So step one, what is the frequency? The frequency is going to be 1.05 times 10 to the 15th inverse seconds. Energy is thus going to be H, which is 6.626 times 10 to the negative 34th joule seconds times the 1.05 times 10 to the 15th inverse seconds. 0.626. Okay. And so that's going to give us the energy. So the energy right there is 6.97 times 10 to the negative 19th. 6.97, assuming I did that right. So that's the first question. What is the energy of the UVB light? The second question is, what is the energy, kinetic energy of the electrons? If I have to subtract the work function of 5.82 times 10 to the negative 20th. So take that, subtract out 582, and you'd get 6.39 times 10 to the negative 19th. I'm not going to ask that second part on the test. Not at all. It's a simple subtraction, yes. but it still confused the living bejesus out of a ton of students. And I'm not going to really worry about it. There's no questions like that on the homework. We're not going to see it on the test. The last question, all of the electromagnetic radiation share the same. Correct answer is maximum velocity. All EM radiation can go at the speed of light. They're all types of light energy. The wavelength depends on what type of electromagnetic radiation. The same thing as the frequency, same thing as the energy. All depend on what we're looking at. But the only thing that's the same is they all are related to the speed of light. Finally, the bonus question, which is Heisenberg is driving a car and pulls over an officer. Do you know how fast you're going? So it says, no, but I know where I am. The officer says, so you're going 50 in a 35. I say, and just great. Now I don't know where. Now I'm lost. The idea, Heisenberg uncertainty principle. You can only know your position or your speed at any given time. The act of measuring one causes you to create inaccuracies in the other. Idea is we cannot measure both at the same time. So I gave them periodic table, all these fun little constants. Give them the conversions. Some of the stuff they didn't really need. Some of this is gas-related stuff. Let's see, the stuff you would have needed would have been below that. C equals lambda nu, E equals H nu. There's that work function thing. There's Beer's law. There's some conversions you don't need. There's H, there's C. There's the conversion of seconds to hertz. All the stuff you will be given. Some of the stuff you won't be given that you don't need. Obviously, I'm not going to share the gas stuff. Okay, let's see if I can open the next. Yeah, all the tests right now are going to be online because of the nasty fact of it's a pain in the ass trying to get you guys all on the same night to come take it. It's even harder now that we have COVID room restrictions. So I figure it's just going to be easier for everyone if we just do it online. You can take it at your own convenience. I don't have to hunt you down. It's just going to be there. So it's written. I need to turn it into the digital version. I'm going to send it out, but it's probably going to be due not this weekend, but next weekend. So today we're going to keep looking at the test. We're not going to finish test. Then we're not going to finish this test 5, whatever. But we can. I can find it. Let's see, recent documents. Let's see. I don't know. We cannot. I mean, we won't finish this today. We'll finish it up on Friday, but Friday we'll also start chapter 6. Chapter 6, mind you, will not be on test 2. But I'm not going to waste all our time. Okay, there we go. Okay. Get this. Let's... As we wait for this to load. Remember, chapter 5, it's all about periodic trends. It's a further analysis of the electron configuration. And it's a little bit about ionic bonding. Not too much. Not too much. There'll be some stuff about Lewis structures on here that we will not have seen. Okay, there we go. Perfect. Okay, so there's only going to be like 5 or 6 questions on this test that we can maybe directly look at. Starting with question 2. Place the elements in order of increasing ionization energy. So let's look where the elements are. Krypton, bismuth, arsenic, and cesium. Krypton is on row 4. Arsenic is row 4. Bismuth is, let's see, where? BI. Okay. Yeah, it's on the 6th. Thank you. Bismuth is, on the 6th, below arsenic, and cesium on the 6th, all the way over. So there's 2 trends at work here. As we move down the table, ionization energy goes down. So the cost of removing an electron goes down. As we move across the table, despite for a couple examples that buck the curve, ionization energy goes up. Ionization energy goes up as we go across the table. That is due to higher Z effective. So just putting them in the order of left to right, we have cesium on the left, bismuth and arsenic above each other, and then krypton all the way on the right. So krypton is the furthest right, cesium is the furthest left. So we've got our ends on that table. Now, when you're comparing bismuth to arsenic, arsenic is higher up on the table. So arsenic would have a higher ionization energy than bismuth. So the correct answer would be cesium, bismuth, arsenic, krypton, or the increasing ionization energy. Note, if I said decreasing, it would be the opposite order. But that is answer C. But so you're looking at the trend. Bottom left, smallest, top right, biggest. So I'm just placing them where they are in the table. If you want to learn the generalized trend, that can work. But if you want to learn, it helps to know why. But if you want to learn just the generalized trend, you can use that. Skipping. Here we go. Part of the following compounds in increasing lattice energy. This one is the first one of, you have to think about this really kind of tricky. MgO, Na2O, NaF, NaI. So let's look at those. For the lattice energy, there's two factors. There's size, and there's charge. Those are going to be the 2 most important things. Size and charge. Charge always takes precedence. So we're going to look at what is the overall charge of all the atoms, and then we'll look at which one's bigger or smaller. The rule is the more charge, the more lattice energy. The other rule is the smaller they are, the more lattice energy. But so first thing is figuring out the charge. So Mg is in column 2. Mg is 2+. O is in column 6 or 16, depending on how you want to put that. But that means oxygen is 2 minus. F is in column 7 or 17, and so is I. So each of those are 1 minus. And sodium is in column 1, so each sodium is plus 1. So just looking at this, magnesium 2 plus, oxygen 2 minus, the overall charge is 4. Sodium plus 1, oxygen 2 minus, the overall charge is 2. 1, 1. I'm multiplying those two charges together. Positive 2, negative 2. Positive 1, negative 2. Positive 1, negative 1. Positive 1, negative 1. So just looking at that, magnesium oxide is going to have the largest lattice energy. Sodium oxide is going to be the second. And it comes down to a fight between sodium fluoride and sodium iodide. Now, in this particular case, you then look which element is bigger. So both of them have sodiums. Both of them have sodiums. So you become with, is fluorine going to be the smaller guy or iodine the smaller guy? The rule of size is size increases down the table. So iodine is the larger element. And so iodine is going to have lower lattice energy. So we're going to have directly in the order I've had it. So you're going to have NaI followed by NaF, followed by sodium oxide, followed by magnesium oxide, or answer D. Answer D in this particular question. That's where we're going to stop today. We're going to end there, but just look at what we have left. What we have left real quick. We're going to look at just a few more questions here. We have question 7, which looks at electron configuration of an ion. We have number 9, about an isoelectronic series. And that may be it. We have a question about electron affinity. So that's number 18. Literally, yeah, we have like 3 questions left. I might do a quick recap after we do those 3 questions, but then we'll be done. So not a whole lot left. With that in mind, I thank you for your time. Have a good day.